Okay, we're started. Action. Okay, so we're starting out here, chapter 14, two variable functions. It's relatively new, but it's the same thing that's going on in one dimension. And hang on, I'm going to pull this a little. Okay, there we are. So here we go. Okay, so recall that in one dimension, a function is a curve. Okay, so that involves an x-axis and a y like that, and then a function is a correspondence between the two of them. All right? So if I were to draw a graph of a set of points that was determined by a curve at every point x, each point x, gives us a point y, and there's the function, right? So now look at it this way too. You could think about x as a distance along a line, and then the y is the distance above the line. So generalizing that picture to two dimensions is really what it's all about. And so here would be the idea that in two dimensions, this then we could think of as a surface or a two-dimensional object above a plane, in the same way that this was a one-dimensional object above a line. Okay? So anyway, just real roughly, I'm not going to get too fancy on these pictures. This is actually a tough section to lecture on in a situation like this, you know, because sometimes it'd be nice to be able to throw up a picture on the overhead camera or something, and you can do that in the classrooms, but here I have no capability for that. So, and I'm a terrible author, but I'm an artist, so that's another thing. It depends on how well people can draw, and I happen to be terrible. But anyway, so now down here, well, the domain, of course, of these functions will be R2, or a subset of R2, strictly speaking, just like a domain here is a piece of the axis that shows up there. So, in this context here, we could say, give something like, and I'm just going to use a really simple picture here so we don't have to struggle, the idea of a surface over the plane, or a piece of the xy plane. That's going to be our two-dimensional generalization of the one-dimensional function, right? And so in this case, we'll then end up with a height for every point, then given a particular point in the plane, say this one here, that's x, and that's y like this, and so you know, that point is the point above it. Where it sits on the surface, which I've drawn as a parabola here, and that'll be one of our main examples, but that's just practice, nothing special about that, right? If I was a better artist, I'd try to draw a little mountain landscape, but I'm not. So anyway, it looks something like this, and so there, again, we have for each point here, you know, the point above it, and that's the function that gives us the height above each point, and that's the corresponding idea up there, right? So this picture that I've drawn here can actually be taken to be that kind of thing, and it's just a circular paraboloid of revolution that sits up there, right? But, of course, evaluating functions works the same way whether we're in one dimension and two. So in this function, say, for example, the value when x and y are both 0 comes out to be 0. If x is 0 and y is 0, then it's 1. Right? If each one were 1, we'd have 2, and so on. So what these things then give, the domain is all of R2. You know, if you have square roots and things, then you got to write out for things like that. But a function is just this geometrical construction. Same kind of object that we have in the one-dimensional case, but now, again, there's 2 points for each domain point, and x and a y. All right? So in general, you know, on a roughly graphing like this is pretty silly. Nowadays, too, of course, everything about graphing is done on computers, and pretty much, you know, MATLAB is the thing you'd want to use. Once again, if I was in the classroom, possibly I might do a little MATLAB, but we won't be doing that right now anyway. But ultimately, that's what you want to do for the graphics. It's just too hard to do any other way. So, of course, why would you want to? So, anyway, there we go. So, the thing about two-dimensional functions, the geometry here is a lot more complicated, and so we need to think about new ways to think about these functions. And we can always graph them like we always have learned to do, and that's a good idea, and everybody should learn some of that. And it's nice with computers, it's so easy to sit down, you can do things like that real quick. So whereas it used to be hard to really find out what the structure of these things are, now it's really not that hard of a hard thing to do, okay? And everybody should get some experience doing it. So anyway, kind of the strategy is to, as we'll see again and again and again as we have, that to try to make sense of higher dimension, do as best you can to reduce it to the lower dimensional case. And typically what that involves here, and I say this a million times when I teach this class, no matter what, that most of the time, two-dimensional calculus is more or less doing one-dimensional calculus twice. Right, so that's what we're doing here, and that's really what so many of the lessons that we should carry off from today include. So anyway, since it's hard to imagine two variables, let's break it up into two one-dimensional sets. So once again, just to keep things simple rather, let's just think of a real simple function, two-dimensional function. These horizontal lines don't help much. Let's get rid of these. Okay, so there's a simple two-dimensional function over a piece of the plane. And of course, it's easy for us to understand what that is. There'd be no need to do this kind of reasoning. This is the only situation we were thinking about. But in this case, but it's not. So the idea is, though, is that this is now a two-dimensional shape. Into different geometries. So in particular here, two dimensions means the structure of this surface, of this thing that I've drawn here, has two kinds of geometry, but it's pretty obvious, right? It's just if you break it up into horizontal and vertical parts, then there's two different kinds of functions. We call these traces, or sometimes sections. Particularly when we're talking about horizontal ones, we talk about contours. So it's just because two-dimensional functions are hard compared to one dimension, so you need all the tools you can get to keep track of them. So here's one tool that we use, but regular graphing like we just talked about are tools that we use. Here's another set of tools that you use. You just need kind of every way to get at it. But anyway, now the vertical cross sections are kind of where I would say, let's set x equal to a constant, x naught say as usual, like this. And so, oops, yeah, and so anyway, if I were to take my shape and project it on that line, the overall shape you're going to get will be this parabolic part to the shape. Okay, so the vertical traces, that's not a very good picture, but that's not a surprise for me, right? So the vertical section of this function is an inverted parabola. And notice that, you know, no matter what kind of, this is a vertical trace above this, a line parallel to the y-axis actually, value of x. It would look the same way if I cut it the other way, right? Part of that's because of this function, but there you go. So anyway, break it up to that. But anyway then, sometimes you'll need other kinds of information. Say, not what it looks like when I slice it up and down, but what it looks like when I slice it sideways. And of course, now these are the idea of the contours, they're the horizontal traces. In this case, it's just a circle. So anyway, for the shape of our paraboloid that we saw last time, like this, the vertical slices are parabolas, the horizontal slices are the contours. That's pretty obvious, but it should make sense that that's how you encode the geometry of these things. Or one way, I should say, not the way, but as one useful way to determine the geometry of these things, right? Anyway, so the horizontal traces, the contours, give rise to what are called contour plots. That are used in topography and geography and things like that. As people who live in the mountain regions, we know all about this. And yeah, well, you know, so the idea is, roughly speaking, something like this. Let me see if I could pull this off. Okay, so hang on, let me take this. All right, so let's say here's a plane that I'm trying to look at. That has this more complicated structure here. So they have not just one hump, but two humps, one that goes up, one that goes down. So there's a hill and a dale in this picture. And hopefully you can see what I'm trying to draw, a big hopefully if there. But now, so anyway, I can kind of see this. I can try and draw it. Maybe I can, maybe I can't. Some people can. But it might be convenient just not to try to represent the three dimensions, but instead you just focus on a horizontal representation of the same thing. And then this bump here, which sticks up, becomes a circle sitting up here like this, with an indication that each circle gets smaller and smaller because it's reaching more of the top of the hill. On the other hand, this one over here then just goes the same way down. If you think about it, let's something like that. So, but when I put those together, I can represent that same information in a two-dimensional representation, and that's the contour plot, the topical representation of the same information. Once again, typically you need everything you can get in this business, so you're happy to have these two different tools that we can use, and you want them, because you need everything you can get, right, for complicated ones. But anyway, I think you've seen these sorts of things, and contour plots of mountain ranges are really interesting. There's some in the book. If I had the book here, I'd throw up a picture there. But you can see what that looks like. It's pretty straightforward. I just wanted one of the tools you need to know about. Okay. Let's just run through a couple more possibilities of things that could happen here that typically can't in higher dimensions, right? Or, I'm sorry, can't in lower dimensions, I should say. Again, you have to give my artwork. I don't know what else to say about this, what I say all the time. So anyway, here we go. Just one more quick example, I guess. If you took sometimes in two dimensions, which you don't have in one dimension, you could have things that are both minima and maxima in some sense. And that's this kind of geometry. And again, I wish I could draw it better. If I start to try to redraw it, I usually mess it up, so I won't try. Anyway, but this guy here, well, you can kind of see here that if I'm in the x direction, f is increasing, but in the y, which is this picture, whereas in the y direction, f is decreasing, which is supposed to be that picture. So this situation should be depicting something like me standing up in Baylor Pass on the Oregon Mountains, say, looking down toward Las Cruces. So then in the west, it goes downhill into Cruces toward the river. Whereas in the y direction, it goes uphill toward El Paso or Tier C, right? And so that's the mountain pass geometry. That is something that happened there, and it's an important thing to be able to take into account. So these are the things that can go on in two dimensions that nothing like that can happen in one dimension. Simply can't. Simply not an option, basically. Okay? So what that tells you too here, is that things like, I mean, not put it this way, I guess, things like derivatives, increasing, decreasing, whether it's a max, whether it's a min, that's going to depend on which way you're going. It's simply not something that can happen in one dimension. Okay? Yeah, but anyway, the derivatives that I'm doing here each way are honestly the same in each direction. You just, again, have to do it twice. You've got to think about what's going on in X and what's going on in Y. And other directions too, of course, because you can have a direction in between X and Y, for example. All right. That's more or less the real rough introduction to 14.1, what a two-dimensional function is. Okay, and some indication of what's going on with these new ones. I'm going to go ahead, and this has been about 20 minutes here, I'm going to go ahead and just stop this right here. We'll call that, I guess, the end of 14.1 for the time being, and I'll come back for the next part in a minute.